Hello everyone. In this video we're going to take a look at the triangle inequality, which states that the absolute value of a plus b is less than or equal to the absolute value of a plus the absolute value of b. Recall that the absolute value of a number a is equal to a if a is greater than or equal to 0, or minus a if a is less than or equal to 0. What this means is that the absolute value of a is always going to be a positive number. From this definition, we can infer that a is equal to its absolute value if a is greater than or equal to 0, or that a is equal to minus its absolute value if a is less than or equal to 0. We can further infer that a lies in the interval between minus absolute value of a and plus absolute value of a. Now, this is a little bit odd in the sense that a will always be equal to here or here, so it'll lie at the two extremes of the interval. It'll never lie kind of inside the interval, but nonetheless, this inequality is perfectly valid. Finally, another way of getting the absolute value of a is to take the square root of a squared, where we understand that the square root really refers strictly to the positive square root, hence the strictly positive here. Okay, so before we look at formal proofs of this inequality, and we will look at two different proofs, let's sniff around a bit and just convince ourselves that this inequality actually makes sense. And we can do that by considering every possible combination of a and b that can actually occur. So here's the inequality again. Absolute value of a plus b less than or equal to the absolute value of a plus the absolute value of b. And the combinations of a and b that can actually occur are as follows. There are four of them. The first one is that a and b are both positive or 0, so greater than or equal to 0. The second one is that a and b are both less than or equal to 0. The third one is that a is positive or 0 and b is negative or 0. And the fourth one is that a is negative or 0 and b is positive or 0. So these four combinations cover all possibilities that can occur for a and b. So in the first situation, where a and b are both greater than or equal to 0, we have that a is equal to its absolute value and b is equal to its absolute value. What this means is that the absolute value of a plus b is equal to the absolute value of a plus absolute value of b. And since all we're doing is summing two positive numbers here, we don't actually need this outer absolute value. So this is simply equal to absolute value of a plus absolute value of b. So we see that the absolute value of a plus b is equal to the absolute value of a plus the absolute value of b, and so equality holds, and we're fine. Now in the second situation, where a and b are both less than or equal to 0, we have that a equals minus its absolute value, and b equals minus its absolute value, which means that the absolute value of a plus b equals the absolute value of minus absolute value of a minus absolute value of b, which is equal to the absolute value of minus absolute value of a plus absolute value of b in brackets, and this is equal to absolute value of a plus absolute value of b. So we can see that once again equality holds and we're fine. In the third situation, a is greater than or equal to 0 and b is less than or equal to 0. Which means that a is equal to its absolute value, but b is equal to minus its absolute value. We then have that the absolute value of a plus b is equal to the absolute value of a minus the absolute value of b, which is always going to be less than or equal to the absolute value of a plus the absolute value of b. Therefore, from the point of view of the triangle inequality, we're fine. Everything is still correct. It's worth taking a moment to think about where this less than or equal sign comes from, and just to convince ourselves that it's actually true. Well, if we draw on a number line its values of absolute value of a and absolute value of b, then this highlighted value here is going to be equal to the distance between these two positive numbers. It doesn't actually matter whether absolute value of a is to the left or to the right of the absolute value of b. This absolute value here is always going to be the positive distance between those two absolute values. On the other hand, if we take a look at the right side, the sum of these two absolute values, they actually represent the sum of this distance, which is the absolute value of A, of this distance, which is the absolute value of B. And the sum of these two distances is always going to be greater than this distance, from which we see that this less than or equal sign actually makes perfect sense. Now, in the fourth situation, the reasoning is exactly identical, and we end up with exactly the same situation, which means that we always find that the triangle inequality holds true. So let's take a look now at a couple of proofs of the triangle inequality. And in the first one, we're going to make use of the fact that A lies between the absolute value of A and minus the absolute value of A. And obviously the same is true for B, right? So B lies between the absolute value of B and minus the absolute value of B. So let's take these two inequalities and add them up. And here we get minus absolute value of A minus absolute value of B is less than or equal to A plus B, which is less than or equal to the absolute value of A plus the absolute value of B. I can then write that minus the absolute value of A plus the absolute value of B is less than or equal to A plus B, which is less than or equal to the absolute value of A plus the absolute value of B. Now, recalling from our first lecture that the inequality x less than or equal to c, where c is greater than or equal to 0, recall it didn't really make much sense to consider c less than 0 because there would never be any value of x that satisfied the inequality. This really means the same thing as x less than or equal to c and greater than or equal to minus c. Well, looking at this and looking at that, we see that they're really very similar, where we can basically consider that this is x, this is minus c, and this is c, which means that what we really have here is an inequality that says the absolute value of x is less than or equal to c, where x is equal to a plus b, and c is equal to absolute value of a plus absolute value of b, which means that the absolute value of a plus b is less than or equal to the absolute value of a plus the absolute value of b. All I've done is I've replaced x by a plus b and c by absolute value of a plus absolute value of b, and there I go. There's my triangle inequality. So a very nice, simple, elegant proof. For our second proof, we're going to start with a plus b all squared, which is equal to a squared plus b squared plus 2ab, which is always less than or equal to the absolute value of a squared plus the absolute value of b squared plus 2 times the absolute value of a times the absolute value of b, which in turn is equal to the absolute value of a plus the absolute value of b all squared. What this means is that a plus b all squared is less than or equal to absolute value of a plus absolute value of b all squared. Now, for the next step, we want to recall that the absolute value of some number, say c, can be obtained by taking the positive square root of c squared. So that means we can go ahead and take the square root on either side here and recognize that this square root is actually the absolute value of a plus b, whereas this one is equal to the absolute value of a plus the absolute value of b. Now, this outer absolute value is actually redundant, right? Because the absolute value of the sum of two positive numbers is just going to be the sum of those two positive numbers, which means that a plus b absolute value is less than absolute value of a plus the absolute value of b, which is, in fact, our triangle inequality that we were trying to prove. Now, this whole proof hinges on the fact that this less than or equal to sign is actually correct. So let's take a look at that more carefully, because we have to convince ourselves that this is indeed the case. So let's take a look at a squared plus b squared plus 2ab and compare it. I'll put the less than or equal to sign in anticipation of what we're going to end up with. So we're going to compare it with the absolute value of a squared plus the absolute value of b squared plus 2 times the absolute value of a times the absolute value of b. Now, a squared equals absolute value of a squared, and b squared equals the absolute value of b squared. Okay, there's just, you take the square, the negatives disappear, and you're all good. So that means that I can cancel out the a squared and the absolute value of a squared and the b squared and the absolute value of b squared, and I'm left with 2ab less than or equal to 2 times the absolute value of a times the absolute value of b. I'll do one more simplification by canceling out the 2's, and I'll end up with ab less than or equal to absolute value of a times the absolute value of b. To convince ourselves that this inequality is correct, all we need to do is recognize that ab is equal to the absolute value of a times the absolute value of b when ab is greater than or equal to 0, and that ab is less than or equal to the absolute value of a times the absolute value of b when ab is less than or equal to 0. Why? Because this is negative and this is positive, and a positive number is always greater than a negative number. And that concludes our second proof of the triangle inequality. So there we go. We've gone through the triangle inequality, which is a very important inequality used in algebra and calculus. There's another version of the inequality which we'll cover in another video.